Hey everyone, good morning. Thanks for coming out. I'm going to apologize in advance. It looks like we're getting a little bit of flicker from my laptop, so hopefully that's not too annoying. My name is Bjorn Hamel. I'm the Chief Security Architect at Workday. And for the last year and a half, I've been spending time in our research area looking at decentralized identity and building various prototypes to learn more about this technology. And so what we're going to talk about today is what problems we're actually solving with self-sovereign identity, what a prototypical SSI architecture looks like, and to truly understand that, we're going to dig into some of the cryptographic primitives and concepts that make SSI possible, and then explore both Hyperledger Indy and how it works to support credentialing, look at a demo that we built using Hyperledger Indy for a cross-company POC, and then we're going to pivot a little bit and look at another research area that we launched where we targeted more open standards and built a proof of concept to show a similar type of credentialing and issuance mechanism. And finally, we're going to compare and contrast those two approaches and see how they're similar and how they're different. So at its core, SSI is really tackling this problem of how do I move verified information from an issuer to an individual and then let that individual share their information onto a particular verifier. So you can imagine some school wanting to confer a transcript, and then that individual wanting to share their transcript with a prospective employer. So the first leg of this journey is not particularly treacherous. These two entities typically have a pre-established relationship, and if there's any errors in the data, the individual can go back to the issuing institution and get their information corrected and reissued. Where things get more exciting is where this individual wants to take their information and share it on to another party that they don't have a trusted relationship with yet. And what's to say, in some cases, that the individual doesn't take some of their data and modify it to better represent themselves for their own personal gain. And so what typically happens is the verifier doesn't actually trust the individual. They go back to the issuing institution, and this is an expensive, slow process. And besides those negative qualities, what might not be immediately obvious is it's also privacy eroding. This issuing institution is now learning something about what that individual wants to do with their data. And so how can we better solve this problem? This is where the core concept really comes through of an SSI architecture to say, what if we had some trusted third party, some way to disintermediate that interaction so that the verifier could look to some source to say, can I trust this data I've just received? And when the issuer provides that data, they could have some way of attesting that it's correct so that it can move securely and in a trustworthy fashion from issuer to individual and then on to verifier. And really at its core, this is what an SSI architecture might look like. And I've called it an entity-controlled identity architecture here because I think self-sovereignty is an overloaded term. It might have government connotations or other things to think that the individual is somehow declaring who they are, a self-attested identity. Really, the cornerstone of this architecture is that we've moved the data and control of the data to the edge of the system. In a traditional architecture, you have a large silo of information that sits in the cloud controlled by some single interest. And in this type of model, we're moving the data and the keys, the private keys, into the control of the individual entities, whether they're issuers or individuals receiving data. And beneath that, we have a protocol layer where we've agreed on standards for how we're going to move that data between the different parties. And really underpinning all of that is a trust layer where we're attesting to a record of keys that guarantee the cryptographic validity of that data as it moves across the network. So our trust layer provides a registry of keys, the shape of data, and potentially a revocation point to guarantee the freshness of data as it's moved throughout the system. And using this type of architecture pattern, in July of last year, we completed a proof of concept between Workday, IBM, ATB Financial, Evernym, and Sovereign, where all of these related interests came together and said, let's try to take this technology and actually put it to use. Let's build a proof of concept where we can take your verified employment information a simulated driver's license, give those as credentials to an individual, and then let those credentials present them in an online banking application to open an account and use those credentials to satisfy your KYC requirements instead of the typical process. And so I'm going to explain architecturally how we actually delivered that and mechanically how it worked. But before we dig into that, to really understand the mechanics of this, we need to go through some core concepts in crypto that were new to me to sort of understand how these mechanics work, as well as how Hyperledger Indy actually works. Because if we don't understand these pieces, then it's really just sort of boxes and lines saying, credential moves from here to there, trust me, it works. So we're going to run through at breakneck speed sort of the 5 really new pillars of crypto or cryptography that I experienced running through this project. The first one were ED 25519 keys. In my previous travels, I had seen lots of RSA key pairs or some elliptic curve cryptography using the NIST P-based curves, but I hadn't actually seen these curves before. And these are really just another asymmetric key scheme using different mathematical functions. And so in this case, the ED are twisted curves in an Edwards system, and curve 25519 are a Montgomery curve. And the real takeaway here is in the same way that you can use RSA keys for sign and verify, or encrypt and decrypt, you use these 2 different key schemes for those operations using this different kind of elliptical curve. And what's particularly interesting is these 2 are birationally equivalent, which means you can start with one of these keys and safely mathematically map it to the other type of key. So you just need one ED key as your starting point for your identifier in these models. Once you have these keys, you can create what's called a crypto box. And this is really a hybrid crypto scheme similar to PGP that lets you symmetrically encrypt a large volume of data and then wrap it asymmetrically with your ED key to send it to another party. Another concept that I arrived upon in this credentialing space were commitments. I had seen sign and verify primitives, encrypt, decrypt, secure random, HMAX, but in the enterprise space, you really don't see commitments come up often. And so what is a cryptographic commitment? It's a new function that takes some type of input, a message, like your salary is $40,000 a year, and a secret, and then puts them into a function to generate and bind those values to a particular commitment. Once you hold that commitment, you can then apply a symmetric function to it called reveal, where you put that original commitment in, plus the message and your secret, and if all those things are still consistent, it will effectively prove that the values haven't been tampered with. And this is particularly useful in schemes where you're issuing in one place and revealing to a verifier in another place. The next crypto primitive that shows up a lot in these schemes is blinding. Blinding is effectively a 2-party computation operation where, let's say I have Alice who has a secret value ABCD, and I have Sandra who has a private key who will act as an oracle to sign values, but you don't want to share your secret value with Sandra, and Sandra doesn't want to give up her private key. So we can use blinding to solve this problem, where we take our secret value, we blind it with a blinding secret, maybe with XOR or something like that. We send it over, send the blinded value to Sandra. Sandra can now perform her signing operation, and then send the signed, blinded value back to Alice. And Alice then performs the opposite, where she unblinds the value to get to the ultimate computed result. So we had 2-party computation to perform that blinding without Sandra ever seeing the secret value that she was performing this operation over. This doesn't work for all types of cryptographic operations, but for ones that are commutative like this, you can absolutely add this blinding step. And the final crypto operation that's important to have some familiarity with is zero knowledge. I've heard it mentioned in a number of talks this week in a number of different levels. This is a great blog post that I found, and it's my take on explaining it quickly as a sort of what we're actually trying to do with zero knowledge. So imagine we have Alice and Bob here, and Bob has solved the Where's Waldo puzzle, and he wants to prove it to Alice, but not ruin the fun of pointing to the page on where the solution is. This is where a zero knowledge proof could come into play to prove that he solved this puzzle. So in this case, he creates a template or a cutout much larger than the puzzle with just a cutout for where Waldo actually is in the page. He then takes the puzzle and affixes it to the back of the sheet so that only the solution shows through the front. So when he turns it around, he can show it to Alice, and she can see, oh, because I can see this cutout, he must have solved the puzzle. But she doesn't know where in the field the solution actually is. So this is effectively what zero knowledge is doing, is it's showing the answer to something without showing the underlying data. And Hyperledger Indy uses a particular kind of zero knowledge that uses multi-party signatures to prove that you know something without actually revealing the thing that you have. And this is the CL signature scheme based on research from Kamenish and his partner. So in this case, awesome. I wasn't going to hazard it. So the verifier sends a challenge to the individual. The individual in this scheme has a master secret, which allows them to then go to effectively an oracle. So again, Bob solved the puzzle. He says, I'd like an attestation from you, oracle, that you agree I've solved the puzzle. And so you send your solution plus your blinded master secret to this oracle. They then have their own secret key. Again, this is an asymmetric key pair. It's a slightly different kind of key. And they take that blinded master secret, they take a signature from their own secret key, and a commitment to say, we commit to the solution being here on the page. And now Bob takes his master secret and effectively unblinds it. So this means that only Bob, because he has that master secret, can take this commitment and do anything with it. And this is effectively like his cryptographic tape to prove or paste to that template that he has the solution. He finally sends this back to the verifier, to Alice. And this is where it's different than the first example I showed you, because not only can Alice see through the cutout that he solved the puzzle, but she also sees effectively this check mark saying there's this party that attests to the truthfulness of this solution. And she can go to some type of repository to look up that public key that goes with that secret key from the issuer, and she can say, yes, I can cryptographically verify that attestation came from this known issuer. So with those mechanics in place, I now want to quickly run through Hyperledger Indy and how it works for credentialing. So effectively, Hyperledger Indy gives us a full stack platform for credentialing. It gives us a blockchain through Indy nodes, it gives us wallets, it gives us a protocol for issuing credentials and exchanging credentials between parties. And if you've heard of Sovereign, Sovereign's not actually a technology. Sovereign is an instance of Hyperledger Indy with some additional governance and frameworks for how they're going to run Hyperledger Indy, or how they're going to run Sovereign using Indy technology. So the first thing we need in any credentialing scheme are identifiers. These are basically the hook that we're going to hang our credentials off of that we might receive. And in this case, this is where these ED keys come into place. The ED key is really the genesis point for your identifier. And when you create your starting identifier, they actually take the lower portion of your public key and turn that into your DID, or your decentralized identifier. There's two kinds of identifiers in Indy. There are pseudonyms, which are created as pairwise connections between different parties, and these never touch the ledger. And then there's verynyms. So a public institution might publish a durable key onto ledger using that verynym, and so it'll write that public key document to be discovered. So once we have identifiers, we can start to connect different parties. And so the way this might work is the issuer has a key, they create a connection request and send it to the individual they want to connect with. The individual can then look up that particular key, verify that it's correct in terms of that DID having been signed properly, and then if they want to connect with them, send the connection response back to proceed with that connection. So once we have two parties connected, we want to be able to credential. And the first step towards credentialing is being able to establish a schema. A schema advertises the shape of data that you're going to credential with. So in this particular case, we have a transcript. And this is really just saying, when I exchange transcript credentials, they're going to have these 6 fields: a name, an identifier, a degree, a year, and so on. And that's written to the ledger in Indy. The next thing I need is a credential definition. And this is really a key management mechanism. When we were looking at that CL signature scheme, and we had that blue secret key for the issuer, this is effectively the way of registering that key so others can look up the public portion of it to verify the validity of the credentials for those signatures. And so with those mechanics in place, we can now issue credentials over that connection that we've established between our individual and our issuer. So the individual actually has to initiate the request because, again, they're sending a blinded version of their master secret to be credentialed over so that the credential can be bound to them. That credential request goes in. The issuer then might verify the facts in their own system of record. They then generate that cryptographic commitment, sign it with their private key for credentialing, record to the ledger the current revocation state. So they might use a cryptographic accumulator to say, this is the current state of the credential, is it revoked or not? And then they return that whole bundle of information back to the individual who can then unblind it with their master secret, and they effectively now hold a credential that's ready to use. And when we say credential data, there's no magic here. It's really just a bundle of JSON with strings. A raw value for the actual string that you received, like someone's name, and an encoded value where every value in their system has to be turned into an integer because the way that cryptography works is it permutes over integers. All of the math is defined over integer fields, so every value that you exchange, whether it's a date, a name, anything else, has to encode to an integer. Cool, so now that we've received credentials, we want to be able to do something with them. And so in this case, we have a verifier who wants to receive that trusted information. So in this case, the flow starts with the verifier, where they send a proof request after connecting with that individual, saying, hey, I want proof of your transcript. And so they send that formatted request in. The individual looks through their local credential wallet and signs a proof request, again, using that master secret to prove that they control the commitments that they've been given before. And then the burden is on the verifier to look up the shape of data to make sure that it's accurate, to look up the credential definition, make sure it cryptographically matches the signature of the underlying commitment they originally received. And then here's an interesting part. They actually need to make a business decision. Do I trust this issuing institution for this kind of data? So maybe for Workday, they would trust it to be authoritative for HR data, but not a university degree. So there's two parts to trust here besides just cryptographic trust. And finally, they check the revocation state and say, has this thing been revoked? And if all three of those things check out, they can effectively proceed to do whatever business process they want based on that trusted data. And to go into a fine point of proof requests themselves, again, it's just a collection of JSON using this framework. And so you can do simple things like ask for someone's name. This says, I don't even care what schema it's from, I just want a name. You can be more specific and say, I'd like you to share your degree, but it has to come from this particular issuer or this particular schema. And this is where things get really fancy. This is where I'm actually sending a zero-knowledge predicate request saying, I want a degree from you. Don't tell me the year you graduated. I only want a degree that's newer than 2010. And so I can send that predicate request, and using their zero-knowledge scheme, I can satisfy that and be able to send the response back without revealing the year that I graduated. So going back to the use case of what we actually built, now that we understand a little bit of the plumbing for how this credentialing system works, this is the area of the system that our team really worked on and built out. And so this is the one I'm going to dig into to look at what credentialing and connection looks like from the Workday system to this individual wallet. So we have our core Workday service. It's predominantly a Java-based service. And so we decided to architecturally create a credentialing sidecar because a lot of the Indy libraries are written in Python and Rust, and it didn't have a great architectural fit. So we put really just an API as an adjunct to that, and then used the Evernym Connect Me wallet for the individual to receive credentials to, and we spoke through the Evernym agency to connect the two parties, and all of this was underpinned by a sovereign testnet. So the first thing we had to do was create a connection to the individual, as you saw. And so we used the agency to establish that connection, which effectively we displayed a QR code in our application. The individual then scanned that QR code and then sent into the agency their own public key that they wanted to connect. Meanwhile, our system was polling for that, and then we received that public key that they wanted to use for their half of the connection and recorded that effectively into our user model, saying this is the DID for this user that we're going to talk to. This is the pseudonym that we'll talk to that user over time. So now we were effectively connected between the two parties. And the next thing that we had to do was actually be able to issue credentials to the user, right? So they have a connection with this user. So we display this new self-service task within Workday that lets someone go and self-service issue themselves an employment credential. So they would navigate to this task, and then the core Workday system would look up that DID that we were storing about the user, look up their employment information, like what was their current title, what was their current salary, and then send this into our sidecar saying we'd like to offer this information to be credentialed to this individual user. And this basically sent a push request to that connected device saying, hey, Workday is offering you the following credential. Do you want to receive it? If they accepted, again, they would send their blinded master secret with respect to that credential back into the agency, which our system would pick up through polling, and then use our private key to sign the final credential and push that back through the agency. And at this point, they ended up with the baked credential in their wallet that they could actually use for future interactions. So lots of boxes and lines and moving parts. Let's look at a demo to see it actually work in action. And hopefully my video will play here. Cool. All right, so on the right, I have the Connect Me wallet. On the left, this is the Workday system where someone's logging into it. And so we're going to do the two operations. The first thing we're going to do is connect the wallet to this person's account in Workday. So they've logged in using some traditional means, and now they have a self-service task to connect their wallet. When they run this task, again, we're sending that back-end request to the agency to establish our half of the connection request, and we're advertising it there for them to scan. They're going to pull that public key information into their local context, into the wallet. And if they proceed with this connection, they've now generated their own key pair, and they're sending that back to the agency to be picked up by Workday to complete that connection. So we now have a pairwise connection between the two parties. And once we've established that connection, we can actually do credentialing. So we created a self-service task for the individual to go in and receive an employment credential. So they're going to go in here now, and they see that they have an issue credential task because they've established a connection. They can pick employment as the type of credential that they want to receive. And then we should see the data. I know it's a little bit small, but there's their salary, their hire date, their title, all of the stuff that you might imagine an HR system of record would be authoritative for. It's then pushed to the device. They can review the credential before they choose to accept it. And again, they're sending their blinded intention to receive it. It's going to the back end. We're signing it. And then it's sending it back to the wallet, back and forth and back and forth. And finally, it should show as received. So let's give it a second. There we go. So they've officially received a credential. They are now in control of this information, and they can share it with whatever party they want to. And so this is where ATB came in and said, what if we change the online bank account flow to accept a verified credential as a way to establish a new account? And so you can see they have a new sign up feature where, again, because they're going to be a verifier in this flow, they first have to establish a connection. So we're establishing that pairwise connection. The wallet's creating yet another public key and private key for just communication with ATB. They're accepting this connection here. And they're now connected with ATB. And the first thing ATB is going to turn around and do is after they get the intention that they want to open a bank account, is they're sending a proof request to the device saying, we need all of this employment information about you in order to establish this account, right? To satisfy that KYC requirement behind the scenes. So the individual can review all of the information that they might need to release to do this, which is quite a bit of information for a banking account. But that's cool. They're going to do it because they want to bank with them. So now they're sending that cryptographic proof in. And then ATB is going to be able to perform those verification steps to look up the credential definition, to decide they trust that key from that Workday tenant. And so they can now see that they've shared that credential. So they have a receipt of that sharing on the wallet. And what's interesting is ATB is turning around and issuing a derived credential. So they're both a verifier and an issuer. They're saying, we're going to give you a credential that's tied to this account that you've just opened with us. So there we go. We've successfully opened a bank account. And what's really cool about what we're able to do with this is, besides the fact that we've just opened the account, we're going to log out. And you saw I didn't establish any password during the sign-up flow, right? I connected with them. We exchanged secure cryptographic information. And now I'm going back to log into my account, and instead of having to establish some password or bind it to email or SMS, if I plug in my account number in an identifier first-based login flow, they can look up in the back end and say, oh, we know the DID of that account. Let's send them a verification request to see that they still control the account credential to be able to subsequently authenticate. And so they're sending proof of control of that account credential to be able to log into that particular account. And so they successfully validated it, and there they go. They've logged in without having ever established a password, and they have successfully shared their credential information to connect. All right. So this is a lot of moving parts. And it was super exciting to see it work in practice. And after we finished all of this work, we sort of took a step back and said, could we do this with a little bit less? Like, what if we got rid of a few things in our drawer that we didn't exactly want to use in the system? And so what we looked towards is an emerging set of open standards, right? As this is late in 2018, DID and W3C verifiable credentials are starting to pick up even more steam, and there's more excitement in the community about them. And we really said, what if we built sort of a custom proof of concept using these two standards? How far could we get towards building a similar credentialing flow? And so that's the next part of the system I'm going to talk about, is what if we just used DIDs and verifiable credentials to perform a similar type of credentialing? So the first standard, again, which lots of people have brought up this week, I think it's fantastic, are DIDs, or decentralized identifiers. And these are really namespaced unique identifiers that point to different ledgers or stores for where that identifier can be resolved. You can almost think of it as like DNS for blockchains. So you might have this UPort DID here that points to Ethereum, or you could have a SOV DID that points to the sovereign mainnet, or even a GitHub DID that points to the GitHub system for your GitHub account. It's really not even specific to a blockchain. It's just a name resolution scheme for identifiers. And when we say identifier, it points to something called a DID document. And a DID document is a format that allows you to advertise one or more public keys that are associated with that identifier. So that if you want to have some cryptographic interaction with that party, you need to be able to look up their public key somewhere in order to do those types of operations. And you can also do additional things like look up a service endpoint and build sort of additional protocols on top of this core DID building block. So the first thing you would need to do in this DID scheme is generate a private key on device and then create that DID doc and send it into some type of ledger to record it so that you can advertise saying, this is my DID doc if you want to interact with me. You can find me by this identifier, and this is my public key. And you could use Fabric or Ethereum or really any type of ledger that can hold on to a value and surface that up for query. Great, so now that we have an identifier or an anchor point, we need some way to issue claims or attributes to the individual. And this is where the W3C Verifiable Credential standard comes in. This gives us a format for moving data from individuals to holders, and then moving data from issuers to holders, and then moving that same data from a holder to a verifier. There's specific protocols for how the format of data should move. And we also need some way to declare the shape of information. So just like in Indy, how we had to register a schema and then a credential definition, in this verifiable credentials model, we need some way to advertise, if we're going to issue transcripts credentials, what's the shape of those credentials. And so you might imagine you could use the ledger to record the schema. There's others who think that you might want to use JSON LD and schema.org to advertise the schema. It's actually not nailed down in the spec as to how you would advertise a schema at this point. But let's imagine that we're going to use the ledger to do this as well. Once we have that in place, once we have a DID for our issuer and a DID for our individual and some type of place where a schema is declared, that's actually all that we need to be able to issue credentials in this model. We can effectively take the data that we have, put it into this declared JSON format, sign it, and move it between parties. And what I want you to really notice here is no data is written to the ledger in this transformation. It's a point-to-point exchange of information between issuer and recipient. And to dig into the credential itself, it's not super scary JSON actually. There's just a couple of things to highlight. There's a credential identifier, which says this is the unique identity for this particular credential. There's the resolution of what schema it belongs to. So whether this is, again, a JSON LD URI or a DID for the schema. The issuer has a DID, so we can go look up the cryptography to make sure the signature of this credential is correct. The holder has a DID, so it binds it to a particular recipient. Of course, we have to have the actual data itself. And then finally, a signature, and this is what proves that the data won't be tampered with as it moves from party to party to party. Cool, so now that we've issued a credential, we want to be able to do something with that credential, right? It's not super exciting to get currency if we can't spend it anywhere. So how does sharing work in this model? Well, there's actually no specification yet for how you challenge someone for a verified credential. There's a lot of different reference ways that people think you might do it, but let's just imagine you put some sort of JSON document out there that says, I want information of these various schema types. They would then scan that with their identity wallet, look for credentials that they have that match, and then create what's called a verifiable presentation. This is effectively taking the original credential or credentials that they received and putting an outer signature on it saying, I control this DID, I'm consenting to share it with you, verifying party. And then the burden is on the verifier to go look up all the key material necessary to verify the series of signatures in this interaction. So they would look up the individual's DID doc to verify that outer signature. They would look up one or more issuer signatures to verify the inner signature on each verifiable credential. And then finally, maybe the schema to verify the shape of data is correct. And last but not least, some type of revocation information. Again, this is open in the spec. This could be a URI, which has maybe a CRL type list of revocation information, or it could be on ledger, where you have the identifiers of all the credentials that the issuer considers revoked. But this is an important check to make sure that the credential is still fresh and can be considered valid. And so if they performed all 4 of those checks, then they can effectively proceed with their business process and allow the transaction to proceed. And you can see it's not really clear here. It's not, my highlighter didn't show up. But this intersection here, this is all the original text that we looked at before. So it's really the verifiable credential wrapped with this outer proof, which is the signature from that individual saying, I control that DID in reference, and I'm choosing to share it in this particular interaction. So that whole inner chunk is the original credential. And then I have a signature from the holder saying, I control the key that goes with the DID that's pinned to that inner credential. And this is my key reference. So it actually doesn't have to be just one key. The DID specification allows an individual to hold multiple DID documents and multiple keys. So there's also a resolver to say which particular key you sign the information with. Cool. So now that we've sort of seen the mechanics of establishing identity, issuing credentials and verifying them, I wanted to show a quick run through from a UX perspective to see how this could work. And so in this particular case, imagine, if you will, we've got a post office who's running this new pilot where if you bring your driver's license in, they'll issue you, the clerk will issue a post office verified credential saying this is your confirmed address. And we've got a demo wallet over here on the right where we can receive these credentials to. So the clerk is typing in this information. They're verifying it's correct with you, and when they hit submit, this is going into some type of credential exchange where the controller of that email can receive that credential if they can prove that they own it. So they've sent that request in. That's effectively created that signed verifiable credential, and now I'm going to relaunch the wallet application over here, and I'm going to authenticate into it, and we see that we have a new verified credential on offer. And so if we engage with that credential, when we hit plus on it, it's actually been added to our local collection of credentials. And so if we go over to the credential section, we should see that we have 2 addresses now, one in Boulder, Colorado, and one in Dublin, California. So I can look at the individual attributes, I can see who it came from, and that's great, we got something. Now I want to be able to share my information. And so I heard that there's this online promotion going on right now where if I share my address, I can get free ice cream, but only if I live in Boulder. So I'm going to go ahead and take my credential, and I'm going to scan this particular challenge. So this is pulling the challenge into the mobile device, and I can see the kind of information they want. They want my verified address, and they're asking, do you have consent to release it? And so I'm going to look through my verified information that I control. In this case, I'm going to say, oh, I want to share my Boulder address, because I definitely want free ice cream. That sounds awesome. And then when I hit confirm, it's sending that, and I hit submit, it's going to sign that with my private key and send that into this service, which now receives my verified information and gives me this coupon I can print out to proceed to get my free ice cream. And to show that trust isn't just cryptographic trust, it's also the business logic that's built on top of this exchange. If I go back in here, scan the QR code again, go through this prompt, and pick my California address instead, and hit confirm, again, it's going to send a verified presentation to the service provider or to the reliant party. The reliant party receives it, and they say, sorry, this promotion is exclusive for your Boulder neighbors. So you can see in both cases, they were valid signed credentials that were sent, but they could then make a business decision based on the trusted data of what to do with it. So why might you...
Just a quick question. Can you get multiple ice creams?
So that's a great question. You could have kept a database of all the DIDs you received to say you'd already seen it before. But if you want free ice cream, we can talk later about that. So Hyperledger Indy. It's a fantastic platform. And they really architected it for the support of pairwise keys to intentionally reduce correlation risk. This is like a cornerstone of the architecture, is we don't want you to be correlatable across all of these connections. And so we've really intentionally put a lot of engineering effort into preventing that. They have very advanced zero-knowledge support. So when I was showing that, degree greater than 2010, that predicate request language is really flexible. You can sort of imagine any number of, if you can create a mathematical inequality, you can challenge for information in zero knowledge using their system. It provides a complete ecosystem out of the box. So you get a ledger, you get a protocol, you get a wallet, everything you could want to get started. I mean, additionally, like Evernym's providing value-added services on top of it to make it even easier, but they really do set out to give you a complete working system. And what's really cool is, like, this stuff's all bleeding edge. It continues to evolve. Like, it didn't even exist when we started this project, but Project Aries has emerged to say, now that W3C credentials have come about and there's more excitement about these standards, they've created Aries to better align their protocols towards the open standards. And the final really important part is that pseudonym model means that no PII has to be written to the ledger. If you're creating pairwise connections and credentialing point to point, you don't have to write that information. On the downside, the crypto is incredibly complex. There's bespoke implementations based on original white papers, and like they've worked with the experts, and it's been audited, and I totally trust it. But it may be difficult if you're working with your security team or you're working with a customer to convince or communicate them to rely on this crypto. Maybe it'd be less difficult 5 years from now, but right now that could still be a tricky part. There's also a lot of moving parts. So the sort of double-edged sword of getting the entire stack out of the box is that some of these parts are at different levels of maturity. So like any open source project, they've done a lot of great work, they've got a lot of different modules out there, but they're not all at the same level of maturity, and some may take a little bit more effort to get up and running in your own local environment. The other thing to note is, for now, the protocol is pretty tied to the ledger. So if you want to use Indy, you're going to be using plenum. There's not really the idea of, well, I'd like to use Indy the protocol, but Fabric the ledger, or public Ethereum. And Aries is, again, moving to abstract the protocol away from the ledger, but sort of current state where things are today, they're pretty well tied together. On the W3C Credentials approach, there's definitely a simpler cryptographic story, right? It's digital signatures. Whether you use ED keys or NIST keys or RSA keys, you're basically saying, the issuer signed this, I signed this, you can trust it. And that's just like digital signatures and all the legality that goes with digital signatures that we've had before. Interoperability is a first-class citizen in this model. So they've really said, we don't imagine there to be one winner or one ledger that will rule them all. It's more like, imagine a world where you have this identity wallet that has DID-based credentials that go to multiple ledgers. I think that's the future that they're painting there, and I think that's particularly compelling. It really is blockchain agnostic. Again, if you look to the GitHub DID method and to other things, they're basically just saying in the specification, you need a registry somewhere that says this identifier maps to this key. Now, DLT makes maybe that guarantee stronger or more secure, but it's not a requirement. And in this model, no claims are written to the ledger. There's still some legality questions around GDPR and DID documents, and there was a good note to that earlier in the week in a couple of panel discussions. I'm not going to jump into that and give legal advice to anyone, but I will just say that it hasn't been finally adjudicated yet. On the downside, correlation is certainly more likely in this model. Whether you have a hierarchical key scheme and you have multiple DID documents, At some point in time, you have a digitally signed document, and if you share that to multiple parties and it has the same identifier, if they collude, correlation is certainly possible. The standards here cover message formats, not protocols. So that whole proof request interaction that I described, there's no spec for how to do that yet. You can certainly fill in the blanks. As you saw in the demo, you can build software to do that. But know that if you move ahead with these types of things, you're probably going to have to do some rewriting to become interoperable. And again, the standards aren't final here. And in my opinion, they're much too open. There's been a lot of academic debate. Should it be JSON LD? Should it be JSON? Should it be JOT? I would love to just move on with it and say, let's just pick one, make a reference standard, and start building towards it. And then open it up to more things later if we actually find that it's necessary. But it feels like there's too many competing interests here right now. And just to put a fine point on correlation of identifiers, if it's not totally clear, because I've heard a lot of people mention correlation this week. There was one talk that was really interesting where they were saying, well, you have to share your email and phone number in all of these type of scenarios anyways, so correlation is going to happen. So when we say correlation of identifier, what we're talking about is if you share some DID associated with a claim on one site, like maybe to make an online alcohol purchase, there could be some evil database that seller is selling your information to, and then when you engage in another site and go to interact with them and present a similar identifier, they could maybe go purchase negative information about you. And what's interesting to think about is claims can also correlate you. It's not just the identifiers. So if I share enough information about myself to have a meaningful transaction, like apply for a job, and then I apply for a mortgage, even if I've got a really fancy crypto scheme to hide my identifiers, you better believe that they can still correlate that that's the same Bjorn across those two interactions. The other question I want to bring up is whether or not we always need zero knowledge. Right? So this is a really fancy cryptographic scheme. This is a really powerful idea that I could have this open language to say, I want new grads only for my application pipeline or whatever it is that you want to do with it. But I think you can actually get pretty far using something called a derived credential. So what if when I issue you an age credential saying this is your actual age, I also give you a credential that says you're over 21. And I give you a credential that says you're under 65. And a credential that says you're over 25. Sort of the common business age brackets for different common interaction use cases. I'd argue that can get you 80% of the way there without any of the complexity of zero knowledge. That's, again, not to say that we shouldn't use zero knowledge. It's just maybe to give pause and say, can we build a simple working thing first, get that out there in the marketplace, and then continue to evolve into zero knowledge schemes later. So my own opinion time, our own experiences between these two projects. Developer time to productivity was much quicker in the second model. We had individuals really struggle getting some of the libraries to compile from Indy and getting other specific details worked out. And we were able to sort of immediately, same day, get people productive in our custom stack using these implementations towards the reference standard. Again, apples to oranges. They were solving sort of different scopes of complexity, but much quicker in the second stack. Generally, when we approached other organizations, because quite frankly, this technology is only interesting when you're building things with other people. When you credential for yourself, it's a lot less interesting. You should just use the database. Those organizations were way more interested in building something that conformed to a standard versus an open source project. Now, certainly I showed you a demo where we all did get together and build towards an open source project. But I'm saying in the broader pattern, because we've talked to a number of parties, they've been more excited about the standards versus the technology. And the final point I want to make really clear is that Indy works. In its current state, you can absolutely build the software that we described. I've been through lots of POCs where the vendor goes back and makes some little tweaks just to make it work for your project. There was none of that for this. We used current trunk version of the software, current release versions. Again, we got a little bit of technical help on getting some of the parts to function, but we use the out-of-the-box software. So it is a mature project. You could definitely get moving forward with it today. And thinking forward about the potential of this technology that we just talked about, one of the most compelling things for me is the potential to deploy strong authentication schemes at scale with this. I mean, if you think about it, effectively in all of these credentialing schemes, we're putting a private key on everyone's mobile phone. This would be a great mechanism to be able to authenticate to different services. And this is really what the DID-auth standard is trying to formalize, to say we can use these keys and this proof of control of these DID documents to authenticate to different systems. So whether or not credentialing really takes hold, and however long that path is, I think maybe the near-term big benefit could be authentication. The other thing that might not be immediately obvious, but is super interesting, is this potential to invert the economics of attack. And what I mean by that is by decentralizing individuals' data into their control, we're moving away from a model where we have these giant honeypots of information, where you have a place where a hacker can say, if I invest enough money, I can get 500 million records, versus I have to invest a certain amount of money and I get one person's record if their data is stored on the device. So I think that's a powerful thing as we start to shift to this decentralized world of personal identity storage. It's going to be the companies that stay behind in the silo world that are going to be the targets of cyber attack over time. And my final thought is, again, from my own personal perspective, I see this as the emergence point of SAML 20 years ago. At that point, we were really just struggling to get things to interoperate. And it was the first sort of exciting touch point of saying, hey, I want to start to do this credentialing thing beyond the boundaries of just my organization. And I think a lot of people are sort of comparing it to maybe OIDC or OAuth, but I think we're actually a step further behind. We're not going to learn how this thing works until we actually get a bunch of integrations out there working. And then we're going to iterate from there. And so what we're seeing now is really just early days, and I think we're going to learn from that, and that'll create a whole new set of standards that follow on to that to refine what it means to move the user into the center of control for their data. So with that, don't take my word for it. You can go try these things out yourself. There's a great walkthrough on Indy that really goes through this whole credentialing example. You can get a Dockerized environment and get Indy up and running for yourself pretty quickly. You can go grab the specs, some assembly required, but again, it's all JSON. So you grab your favorite programming language and crypto support for digital signatures, and I bet you could get a proof of concept going pretty quickly yourself. Thanks for your time, everyone.